Okay, so last section we talked about exponential functions and how they sort of relate in our big picture of college algebra. And now, because we've already talked about inverse functions, we will talk about its inverse, which is the logarithmic functions. And so the key thing to remember, as we'll talk about later today, is that they are inverse functions. So exponential functions are inverses of logs, and so all the rules that apply to the inverse functions will apply in this situation here. So an exponential function was written and defined in the last section. So a logarithmic function is written in the following form. So you have y equals, and then you're going to write literally the word log, and then there's going to be a little subscript, which we'll call the letter a, and we'll talk about that in just a second, and then the variable x. So log base a is how you say this, and so therefore that suggests that a is the base, right? So just like in an exponential function, you had a base raised to a power, we're rewriting it in this case so that the base is now a subscript. And keep in mind, a must always be greater than 1, okay? Okay, so the big thing with the section dealing with logarithmic functions as it relates to exponential functions is the following definition. So if we have our log definition, log base a of x can be rewritten where a is your base to the y power equals x. So just like when we talked about in exponential functions, the base a in an exponential function is the base in the log as the subscript. All right, so you can kind of think of this almost as a loop. So the base a is raised to the y power, so y is basically defined as an exponent, and that's going to equal x. All right, so keep in mind y is always the exponent when it's written this way, okay? So that's sort of the first skill you have to make sure you understand is can you convert from log form to exponential form? And doing so will save you lots of time and anxiety as you try to solve a lot of these equations, okay? So as it's related to its inverse, of course, the domain and range are also reversed, right? Inverses mean the x things and the y things are switched. So basically what we're saying here is if the domain of an exponential function was 0 to infinity, the range of the exponential function was 0 to infinity. The domain of the log function is 0 to infinity. And therefore, the range here is all real numbers. All right, and so when we talk about the graph, we'll see how that applies, right? If you think about an exponential function that we talked about last time, the domain was all real numbers. So because it's the inverse, it now becomes the range. And the range of this function was greater than 0. And so that becomes the domain of this function. So we're going to keep that in mind as we do a bunch of other stuff, okay? So the first skill I mentioned is kind of being able to convert from exponential to logarithmic form. And so that's what this first example is all about, right? So we know, as sort of an initial example, that 2 to the 4th equals 16, right? 2 to the 4th is 16. No problem there. When you write it in logarithmic form, the base is going to be that 2. So you're going to write it as log base 2, and then the 16 goes right after it, right? The exponent is 4, and so the 4 is going to become isolated and what it equals on the other side, okay? So the base is 2 in both cases, the exponent is 4 in both cases. And that's the idea behind all of this, all right? So log base 1.2 of x equals 3, right? As long as you know that that exponent is set equal on its own, then you're in good shape. The one base that's sort of interesting is log base e, and we talked about it in exponential functions and really didn't do much with it there. But when we talk about it in log form, this is what happens. When you write it as log form, it's log base e, the 9 is there, and your exponent is b. But because e is sort of a significant number in the world of business and other things, it gets its own special log notation. And so what you'll often see and what you'll be expected to write is instead of log base e, you'll write it as ln, which is Latin initials for natural log, right? And so you'll write it as ln9 equals b. So just know that ln and log base e are literally the same thing, but we do want you to write log base e as ln in practice, okay? So writing the last one here, we have log, your base is the variable a, the number is 24, and the exponent is 4, okay? So hopefully that skill's pretty straightforward, and you'll see this a lot in later sections, okay? So if we can go from exponential form to logarithmic form, we should go the other way. All right, so here's the base is 3, the exponent is 2. And so you can kind of think of it as like a little loop, 3 squared equals 9. And that's a good way to check because we know the 3 squared is 9. So if you had written it another way, it wouldn't be equal. So that's a good check when we have numbers that are familiar to us. All right, and then moving along, a to the 5th power equals 4. There's no number in this log, so that's kind of another interesting scenario. When there's no number written as a subscript, it's automatically implied as a base equal to 10. Right? Just like an exponent, when an x without an exponent is implied to be a 1, or a number in front of the x that has no number is a 1, the base, when there's no number, is implied to be a 10. So whenever you see a log without a number, don't think it's a typo. It's a base 10 that's implied. So you'll write this as 10 to the negative 8 equals x. All right? And then, again, whether you see this as log base e of x or ln of x, you'll see it either way. You'll probably see it more as ln of x. But just know that it's log base e to the negative 3rd power equals x. Okay, so those are the basic conversions. It gets a little bit more involved when we have sort of order of operations, if you will. And so it's no different than the other examples. It's just got some other things that we've got to keep in mind, okay? And so we'll take a look at these next examples, but the process is the same. You're still going to take the base and write it with an exponent, and then you'll write the exponent on the other side, okay? And so let's take a look at some of these. Base 4, so 4 to the x equals y plus 3. Notice that y plus 3 is in parentheses. And so you want to make sure y is by itself, right? So we're solving for y, so bring the 3 over to the other side, and there's your exponential function, right? So just get y by itself, just like you would in any other scenario, and you're okay. All right, so here there's no parentheses, so you want to move the 1 over first and get the y by itself, right? So notice here the y was connected in parentheses. Here it's not connected in parentheses. And so bring the 1 to the other side. Your base, remember, is e when you have ln. So e to the x minus 1 exponent equals y. And that's the idea, okay? And then moving on with some of these others, the 7 is on its own, so you can bring the 7 over. Y minus 2 equals x minus 7. And now we have y minus 2 in parentheses, so that comes together. So the base is 2, your exponent is x minus 7, and then everything in parentheses is on the right. And bring the y by itself, so add the 2 back to the left. All right, and so that's how you solve for y in that case. And then finally, we have a little negative, which sort of throws a little loop into things. So we're going to take the same idea, where we're going to bring this negative 3. It's not in parentheses, so move that over. We'll worry about the negative in just a second. So x plus 3. And now we can take and divide by a negative 1. So think of this as a negative 1 in front of the log. And then if you divide by a negative 1, you have log base 3 of y equals negative x plus 3. So you can kind of write it like that. You can distribute the negative if you like, but then it's log base 3. There's your exponent on the right, and that equals y, okay? So whether you distribute the negative or not, it's up to you, but that's sort of the idea. All right, so those are the ideas of just rewriting things. We haven't really solved too much. We haven't solved an equation yet. We've just sort of used the process of rewriting these exponential functions and logarithmic functions just to get used to the idea. So we'll see how that does, how that applies to when we actually evaluate them and get numbers, okay? okay? So if we look at the next section, you don't really see an equation. It's written as an expression, but you can sort of think of it as an equation. So what I like to do is set everything equal to y anyway. So log base 2 of 16, now you can do that on your calculator, but we want to get used to you using the rewriting of the expression. So we need an exponent, so I'm going to call that exponent y. So if you write 2 to the y equals 16, you can sort of use some of the rules we used in the exponential section last time and solve for y. All right, 16 can be rewritten as 2 to the 4th, and so y is 4. And in a little bit, I'll show you how to use your calculator so you can get all of these things. All right, but just make sure you know how to rewrite them. So always come up with an exponent, so 3 to the y equals 1 over 27, and you can think of this as 27 to the negative 1, which means that 27 can be written as 3 to the 3rd to the negative 1, and 3 times negative 1, as you remember from last section, is negative 3. Okay? Now on your calculator, I think there is an option to write something as a log base. So let me see if I can find that on the calculator. It should be one of these alpha buttons. Let's see if I can find it on here. Let's see. So if I look at alpha window, here we go. So on your calculator, I knew it was here somewhere. So on your calculator, if you go to alpha window, you'll see option 5. Log base is what you can use to write your answers here. So let's get rid of some of this. Let's clear that out. Let's try that again. Alpha window, option 5, log base. And what you can do is you can simply type in the numbers. So log base 3, and then you can type 1 divided by 27 there, and press enter, and you get your answer. So that's sort of a quick way to do it. If you had to do something very fast, maybe it's Math Excel, and you just had to get the answer, okay? But this is the process that we want you to show when you're rewriting the functions. All right, so you can set that equal to y. You have 1/4 to the y equals 4,096. And again, you probably don't want to sit here and figure out what the exponent is raised to. So you can go to your calculator, go to alpha window 5, log base 1/4 of 4,096 is going to give you -6. Okay? So if you raise 4,096 to the -6th power, you would get 1/4. And so y equals -6. So that's kind of a nice shortcut there. And just to drive this point home, when you have a square root, or in this case a cube root, we have the natural log. So you can write this as log base e if it helps you to write that there. And then you can write this as the cube root of e, and you can set that equal to y. And then if you want, you can write e to the y equals the cube root of e. Now, if you remember what the cube root is written as a fraction, this becomes very easy. So e to the 1/3 is what a cube root is, and so your answer is going to be 1/3. All right. There is a button on your calculator. So again, going to your calculator, you could find the ln button. And then if you find your cube root button, which is under your math option, you can go to cube root, and then you can put in e. And the E button is the second division sign, right? And then you can close your parentheses there, and it will give you a decimal, which of course you can make a fraction, and it'll be 1/3. All right, so there's a couple things that you can do on your calculator to make this a little more straightforward, okay? So here we're going to have you actually use your calculator to find them, and you'll have decimals for each of these things. So again, go into your calculator. You have ln, and then you can just type 15 divided by 4, and there's your answer of 1.32. So just write that. You can round it to maybe 2 decimal places. It's probably good enough, 1.32. And then they just get kind of silly. So you have like some fraction here where you have the log of 23 over 14 divided by -0.01. So that's just more of an exercise in finding the buttons on your calculator. All right, so you can round it to 2 decimal places there, and then do the same thing over here. And so it's just a lot more stuff to type in your calculator, but if you type all of this in on your calculator, you should get 1.11, okay? So pretty straightforward, and I think you'll be okay there. The next little section talks about the domain. So we talked a little bit about the domain here in a general, a parent logarithmic function where it's 0 to infinity, but that all relies on what's inside the parentheses. And so if you just have your basic log of x function, then this tells you that x is greater than 0. But when you have parentheses implied with it, the whole thing is greater than 0. So the domain is simply whatever's inside the parentheses of the log greater than 0. And that's it. Right? So x is greater than -3, or you can write this as -3 to infinity. So these are just like all the translations that we've done in previous sections, straightforward there. All right, there's no parentheses here, so you can ignore the 2, but the x cubed gets it, right? So x cubed has to be positive, and so when you take the cube root, right, the cube root of x, cube root of 0, well, the cube root of 0, of course, is just 0, and so that stays. So the thing I wanted to point out with this example is that you have to pay attention to your parentheses, right? So when you have parentheses, you want to make sure the whole thing gets set greater than 0, and if it doesn't, you just focus on the variable. All right, so this leads us finally into our graphs, right? So just like exponential functions, logarithmic functions have some standard graphs, and so we'll do some basic ideas along with some of the translations that come into this situation. So we talked last section about the points that are always on exponential functions. Well, since they're inverses, you're going to see the opposite in terms of x and y here. So whereas an exponential function always contained 0, 1, logarithmic functions always contain 1, 0. Exponential functions always contained 1, comma a. Well, log functions are a, comma 1. And same thing with its reciprocal, okay? So all we did from the last section is reverse x and y. In an exponential function, the asymptote was at y equals 0. It was a horizontal line. Here, I'm sorry, this is a vertical asymptote. Sorry, I typed that wrong. So that's going to be a vertical asymptote at x equals 0, right? So we have a log function. It's going to be vertical. All right, and so what we're going to say here is that the graph always increases as long as that base is greater than 1, and it will always decrease when the base is between 0 and 1, okay? And so that should set us up for some of our graphs. So I'm just going to do one sort of standard parent function, exponential function compared with its log function, so you can see just in fact how it is related as inverses. So here's our exponential function from 6.3, and here's our log function in 6.4. What we talked about last class was that the domain of exponential functions are always all real numbers, and the range is always 0 to infinity. So there is no x-intercept when we talk about an exponential, and the y-intercept is always 1. The asymptote is y equals 0. And this is what we talked about last class. So if the blue graph here that I'm drawing is your exponential function, when x is 0, y is 1, right? When x is 1, y is 3. When x is 2, y is 9, etc., etc. So you can graph this 1, 3, 2, 6, 7, 8, 9, somewhere up here, and we have our exponential function. All right, so with the log function, it's the inverse, so everything is switched. So the domain now becomes 0 to infinity, the range becomes -infinity to infinity, the x-intercept now becomes 1, 0, right? You switch the x and the y, and the y-intercept now ceases to exist, right? They reverse, and the asymptote again switches your axis. So if I use a different color to draw that, I'm going to have a vertical asymptote here, and then my points are going to be reversed. So instead of 0, 1, you're going to have 1, 0. Instead of 1, 3, you're going to have 3, 1. Instead of 2, 9, you're going to have 9, 2. So 1, 0, 3, 1, 5, 6, 7, 8, 9, 2. Okay, and there's your log function. And what's always true is that you're going to have this y equals x line as sort of a reflection, right? So y equals x is always going to be the axis which you sort of reflect it over, all right? So hopefully that makes sense. And the key thing, of course, is that you're always going to reverse x and y. So if you can graph an exponential function, you just flip x and y so that you get your logarithmic function. And that's the key idea. All right, so we're going to take that idea and now apply it to some of the more translated graphs. And so I have a few here. There's a few parts to it, but it sort of sets up what you'll do in Math Excel. All right, so if we take a log function and we have log base 3 of x plus 1, the domain we just talked about is when x plus 1 is greater than 0. And so that means x is greater than negative 1. And you can write this in interval notation if you'd like, but I just want to set the variables good. And then the range, we already talked about. The range of any log function is going to be all real numbers. Okay, that will never change. Now to find the inverse, this sort of harkens back to the last unit, right? So what we're going to do, just like we do with any inverse function, is we're going to replace f of x with y. And then we're going to switch x and y, right? So x equals log base 3 of y plus 1. And now you're going to solve for y. Because we already know how to convert from log form to exponential form, this is going to make things a lot easier. So your base is 3, your exponent is x, and that's going to equal y plus 1. And that is the big step to go from log form to exponential form. So when you find inverses, and you'll be finding plenty of them, you want to make sure you convert from your log form to your exponential form. It makes things extremely easy to solve, and then you set y equal, so you subtract the 1, and there you go. If you don't convert it from log to exponential, you're going to be lost and just kind of stuck in this little loop of not knowing what to do. So make sure you can convert from log to exponential, and then because the inverse of a log is an exponential, the final answer should be an exponential function, all right? And so there you go. There's your exponential. If you want to write it as f inverse, you can, but the domain is going to be all real numbers, just like every exponential function, and the range is going to go down by 1, and so y is greater than negative 1, right? This graph shifts down 1. Or, of course, you can look at the domain of the log function and rewrite it as the range of the exponential, okay? They're all interrelated, so the more patterns you can see developing, the better it is. And so just as extra practice, we're going to have you graph these as well. The easiest way I would suggest is for you to plot points, all right? So if you go to your graph and type in your two equations, y equals log base 3. So we'll do our alpha window, log base 3 of x plus 1. What you'll see here is that some of the numbers aren't so easy to graph. So if you look at your table, you see a 1, which is great. So 2, 1 is one of the points you can use, but then we don't have another point again until 8, 2. So those are the points. I would look for integer values as often as possible, and you'll be okay. So 2, 1, 0, 0, and 8, 2 are the ones that you'll see. All right, so we're going to graph that over here. So I'll just put these numbers here for x and y. We have 0, 0, 2, 1, and 8, 2. And so when you graph these, you're going to have 0, 0, 2, 1, 8, 2. All right? And you know for your log function that the domain is going to be x is greater than negative 1. So you're going to have a vertical asymptote at x equals negative 1. And then graph that, and there's your log function. Now you could use your calculator to retype the inverse function for the exponential, or you can just remember that the x's and the y's are switched for the inverse. So 0, 0 stays, but 2, 1 becomes 1, 2, and 8, 2 becomes 2, 8. And so you're going to have a vertical asymptote become horizontal at negative 1, 0, 0, 1, 2, and 2, 8. All right, and that's the idea. So these graphs get a little cluttered, but hopefully you can kind of see what's going on, all right? And so the same process applies for other functions. The only difference with the next two are we have a log function here, and then we have a third function with e as your base. So I'll just do the algebra, and then I'll trust that you can plot these on your calculator. And if we need to use decimals, we use decimals, all right? So the domain of any log function, right, there's no parentheses here, so it's just gonna stay x greater than 0. And your range is always gonna be negative infinity to infinity. So before you even solve for the inverse, you already know the domain and range of it, right? The domain is gonna be all real numbers, and the range is gonna be y is greater than 0, right? So you don't even need to know how to do the inverse to get the domain and range, all right? But to do the inverse, we do the process that we just did by switching x and y. So y equals ln x plus 1, switch x and y. There's no parentheses, so get the y by itself, subtract 1. And when you have the ln of y by itself, you have to reverse the base and make it exponential. The base, again, is e, right? You have natural log. So e to the x minus 1 equals y, and there's your inverse function, all right? That's your inverse. And then you can graph that below. Looking at your calculator, when you do the log graph, there's a lot of decimals here because we have e, so we'll just kind of approximate it. At 2, you have about 1.7. At 3, you have about 2.1. And so you're going to graph that, okay? So 1, 1, 2 at 1.7. Again, we're just approximating it. 3 is about 2.1. And we're going to have sort of this idea here, right? We're going to have our vertical asymptote, and then you reverse it for the inverse. Okay, so 1, 1 stays. We're gonna have a horizontal asymptote here. 1.7 is x, 2 is y, 2.1 is x, 3 is y, and so you get something like this. The good news is on MathXL, you'll just have to do this as a multiple choice. So you can just pick some from the list of options, all right? So that's the idea. And so we'll end this little graphing section with an exponential function, all right? And so, again, if you think about our exponential functions from the previous section, we know the domain is all real numbers. And then this -6 means the graph is gonna shift down 6. So our range is gonna be greater than -6, all right? And so, of course, you'll have an asymptote there, etc. Just quickly moving to D and E, the domain then becomes x is greater than -6, and the range is all real numbers, right? We're just going to reverse them. And then we can find the inverse. So y equals e to the x plus 1 minus 6. Switch x and y. We're going to add 6 to get the y by itself. And now it's in exponential form. So you've got to put it in the other form. So what's the base? The base is e, so I'll write that as ln. And then you have x plus 6, and your exponent is what's left. And so then just solve for y. And finally we have ln of x plus 6 minus 1. All right? And that is your inverse. And again, graphing, it's not the most straightforward option, but you can use your calculator to plot points. All right? And so when I do that, I'm going to use my exponential graph and type that in. And I'll have, let me move this over so it's a little bit more room for the graph. We'll have x and y up here. So -1 gives you -5. 0 is -3.28. And 1 is 1.4. Again, I get all these from my calculator. I'm not going to show you how to do that on here because I think you get the idea. So -1, -5, 0, somewhere -3.28. And then at 1, it's 1.4. And so you have a general idea here. So our asymptote is at -6. And your graph will look vaguely like this. Now there's your exponential function. And then switch them for your log function, right? So now our vertical asymptote goes there, and then we're going to flip the points. -5, -1, -3.280, 1.41, and then you can plot them, right? So again, it looks a little bit, busy, but I think you'll get the general idea. Just plot points and you'll be okay. And on the test, I don't know if we'll have you graph both of them. We may just have you graph them separately. But as long as you can plot points, you should be okay. All right, our last set of examples is just solving a whole bunch of logarithmic equations. All right, and this is sort of the key algebraic aspect of this section. So if you can convert everything from log to exponential and vice versa, you should be okay. All of the examples here are written in log form, so if you can write them in exponential form, it's a lot easier to solve. All right, and so we're just going to keep rewriting everything over and over, and that's solving for the variable. So the base is 3. 3 to the second power is 4x minus 7, and the rest should be pretty straightforward. Add 7, divide by 4, x equals 4. Okay, that's all you're doing. Some of these get a little bit more involved, as you'll see later on, but that's the basic idea. Here the base is x. X squared is 64. Now technically when you take the square root of both sides, you would take plus or minus. And so you logically would say, x is plus or minus 8, which isn't incorrect, but keep in mind that a base of a log can't be negative. You can't have the log base -8. So we're only going to look at the positive aspect. So the only correct answer is positive 8. Okay, so keep that in mind. It's a little nuance, but keep that in mind whenever you're finding the base has to be positive. All right, here we have ln, so base e to the 11th is e to the x, right? This whole thing, it goes over there. Well, that's pretty easy. X has to equal 11, right? The bases are the same. Pretty straightforward. 3 to the x equals 81. This kind of reverts back to last section when we try to figure out base 3 to what power gives you 81, and it turns out that 3 to the 4th is 81, right? So there's a little bit of review from what we did last section. We get a little bit more involved with some quadratics down here, but nothing that you can't handle. 2 to the 4th equals x squared minus 2, and now set it equal to 0 and solve, right? 2 to the 4th is 16. You're going to bring the 16 over. So we have, actually you could factor it, but add the 2. It's probably easier to write it this way. X squared equals 18. Square root of 18 is x. And you can simplify that to plus or minus 3 root 2. Now keep in mind, we include both answers in this case, right? We weren't trying to find the base. The base is already 2. We're good. The base is positive. That's not a problem. So then we just go back to our conventional solving. 2 answers plus or minus 3 root 2. All right, f, 3 squared equals this quadratic. This looks like we'll have to factor it based on how it's written. 3 squared is 9. And now we just use good old quadratic techniques. Set it equal to 0, and you'll have to factor. 3 minus 9 is 6, -6. And you get what? X minus 1, x plus 6, and set that equal to 0, x equals 1, and x equals -6. And then finally, 4 to the -8th equals 16 to the x, and that's one of those where we try to find the same base, right? So write that as 4 to the -8. 16 is really 4 squared, and then you can use your property of multiplication of the exponents, and so -8 equals 2 times x equals -4. Right, so the algebra I don't think is terribly difficult for these. You just have to know how to convert from exponential to logarithmic and vice versa. That is probably the one skill that you will need to be successful for this section. And if you can master that skill, this section is very easy. All right, so you should be good to do all the Math Excel, and we're all set.